Being communication engineers, filter circuits are very important to us, especially which deals with radio frequency, microwave systems. But unfortunately, ordinary electrical cables cannot carry high-frequency current, as it leads to energy loss and signal reflection. So it was important to use another specialized cables to conduct electromagnetic waves. These special cables called transmission lines. In order to describe the propagation of the information between two or more locations, we have to study the behavior of the transmission lines by describing both voltage and current with respect to the space and time. And such behavior is described by a pair of coupled linear partial differential equations called Telegraph's equations. But first let's think about something interesting, which is why they developed the theory of transmission lines. To know the answer of this question we need to go a little bit deep in history. Earlier in 1816, Francis Ronald observed some electrical problems were retarded in passing through in isolated wires. But they didn't know what caused it. In 1831 Michael Faraday showed that this effect was caused by capacitance between the wire and the earth or water surrounding it, which is now referred to as Faraday's law of induction. After many attempts to solve this problem, they reached that early cable designs failed to analyze these effects correctly, and a suggested solution was to use a higher voltage and a larger cable. But Lord Kelvin believed that his law of squares showed that retardation could not be overcome by a higher voltage. So he designed a complex electric field generator that minimized current by resonating the cable, and a sensitive light beam mirror galvanometer for detecting the faint telegraph signals. And in 1855, Lord Kelvin formulated a model for the current diffusion in a submarine cable based on their capacitance and resistance, but since long submarine cables operated at slow rates, he did not include the effects of inductance. By the 1890s, Oliver Heaviside had produced the modern general form of the Telegraph's equations, which included the effects of inductance and which were essential to extending the theory of transmission lines to the higher frequencies required for high-speed data and voice. Now we want to model the transmission line we want. Take delta x of the line. So if we take this delta x, we will get something like the figure, where R is the resistance of the conductors. L is due to the magnetic field around the wires, self-inductance. C is the capacitance between the two conductors, is represented by a shunt capacitor. The conductance G of the dielectric material separating the two conductors. First, if we take KVL equation, then we get this first equation. By making delta x go to 0, then we get this equation. Second, if we take KCL equation at red node in the figure, we get this equation. By making delta x go to 0, then we get this equation. We can combine them by differentiating one with respect to time and two with respect to x, then we get the final equations.
For our solution methodology of Telegraph's equations, we have used separation of variables method as an analytical solution for the equations. We started by detecting our boundary and initial conditions to use them to get the final solution. This models a telegraph wire of length L having the voltage at both ends x equals 0, and x equals L, clamped at 0. The initial conditions, 4, and 5, represents an idealized signal consisting of a spike at x equals A, that is stationary at time 0. Now for solving the equation we will have our following assumption. U of x and t equals x of x times t of t. As the main assumption for separation of variable method, by moving on for our analysis we will get to our first equation. Then we impose the boundary conditions 2 and 3 to get the following equation. After that we will use our initial conditions 4 and 5 to get the values of the parameter of the equations to reach our final solution.
As G increases, the losses increase, in the dielectric, where the amplitude delivered at far end of the transmission line is about 3 times 10 power negative 10, which is approximately equal to 0. And this result was expected. Changing RL doesn't affect neither the voltage across the transmission line nor the voltage at near end of the line. But it affects the amplitude of the voltage delivered at the far end. Changing Z affects the amplitude at the near end. And accordingly the amplitude across the line and the far end are affected as well. As Z increases, the amplitude decreases.
So, early explained what a transmission line is. Its structure and length made us wonder if we impose a time-varying voltage on one side of the transmission line, which is the input, what happens on the other side, which is the output. The telegrapher's equations came from a transmission line model in order to answer this question, where when we solve the telegrapher's equations for some data, the effect of the wire parameters becomes obvious and the behavior of the transmission line is predictable. Now, we can see how important the telegrapher's equations are in the communications industry.